Hello everybody. My name is Xiang Li. I'm a postdoc fellow at the IMS Center at the University of Cincinnati. And this lecture is a special topic in the Industrial Big Data course. Now that we have learned many machine learning algorithms and their applications in the predictive maintenance text, and in the following I will talk about more advanced data-driven technique. It is about the introduction of deep learning and the transfer learning in the industries. So deep learning has been very popular in the recent years, but it is really not very new. Actually, it has been developed over many decades. So the biggest concept is the artificial intelligence, and it refers to any programs that can sense, reason, act, and adapt in many applications. And within the artificial intelligence, we got many machine learning algorithms. And machine learning is basically a tool to realize the artificial intelligence. And among many machine learning techniques, we got deep learning. It is just one tool in machine learning. And it is not very complicated. So the left figure is about the basic concept of deep learning, which is also known as a deep neural network. It connects many neurons in the model and do the reasoning, do the inference, something like that. And the lower left figure is a typical model of the deep learning stuff. It is about the digit recognition. So we are given the input of the image like the digit 3, and we use the model to directly do the recognition. Oh, and we know, oh, it is the number 3. So it is a very straightforward and actually very simple technology. So why do we need deep learning? We have learned many machine learning algorithms such as SVM, SOM, and maybe the more simple, the linear regression, something like that. But the typical way of many machine learning algorithms is like this. First, we are given the input. Maybe we want to recognize what the image is. It is a car. But we don't actually take the raw input as the input to the model. First, we do the feature extraction. We may extract some manually designed features for our recognition. Maybe we'll know how many wheels is in the picture, is there glass in the picture, something like that, some features. And we use that features to be the input to our deep learning model. Sorry, to input to the machine learning model. It is a classification task, and we use the features as input, and the classification model will give us the output. Oh, it is a car. So the flowchart is we got the input, and we extract features, and then we do classification. So there is a very important step in here is that we need to do the feature extraction by our hand, or we need the manually designed features. But using deep learning, it is more simplified. So we are still given the input, the car image. We don't need to do feature extraction. We just put the raw image as the input to our deep learning model, and then the model will directly tell us it is a car or not. So we don't need to manually design any features. It is a very automatic. So the whole flowchart is very straightforward and simple. So that doesn't need much prior knowledge, expertise on the signal processing or something like that. So it is a very straightforward workflow. And deep learning also has many advanced merits. Uh, in comparison, when the data amount is not very large, we see that deep learning and most machine learning algorithms basically achieve very similar performance. But now that we are in the era of big data, so we know that deep learning in the condition that we have large amounts of data, the deep learning will significantly outperform the other machine learning methods. So that's why we need deep learning. And this is also another comparison of traditional machine learning and deep learning algorithm. For example, we are given the task of recognize the image, what the animal is the image. It is of course a cat. And then we are given the image. First, for the traditional machine learning methods, we will have to use the handcrafted features. We need to extract some features like how many eyes in it, or what color is it, some features like that. And we use the features as input to feed into a simple classifier. Then we get the output. But for deep learning, it is more automatic. We'll just use the raw data, the raw image as the input, and directly feed it into the deep learning model. And the model will automatically learn many levels of features. For example, the low-level features, mid-level features, high-level features. The model learns all the features by themselves, so we don't need to give some knowledge to the model. He just learns by itself. And the knowledge it learns is not meaningless. It actually has some physical meaning. For instance, in this text, we are given the image of a cat. And the low-level features correspond to some very basic features. We can see here the visualizations. It's like some edges and even colors here for the basic features. So the model will know we need the low-level features as the basics for the identification. And for the mid-level features, we can see some meaningful shapes like a curve. This is a round, and also many complicated color patterns here. It is a mid-level features. And about the high-level features, we can see that there is actually very meaningful and abstract shapes here. It's like this may be an eye of the cat, and this is a edge of the image, something like that. So the model will learn all the level of different features by itself. It's very straightforward. And why not we use deep learning? We know that deep learning has achieved many advanced performance in many applications, such as the image recognition. Every time we go to the airport, we will have our face recognized. The most efficient algorithm is deep learning, and also the video surveillance and even the basic transformation from the voice to text and the robotics about maybe the most popular now is Boston Dynamics. And one of the most famous application is the Go game, the AlphaGo. They beat the best human player in the Go game. So deep learning has achieved many success in different areas. And why not? Deep learning and deep neural network has been developed for many decades, actually, about 3 decades. But why is it now so popular in the recent years? There are mainly three reasons. One is the access to the industrial big data. Many decades ago, we know that the model, the neural network, can do a lot of stuff, but we don't have sufficient data. Nowadays, the sensing technology has been well developed. We can collect many different condition monitoring data for our analysis, and we can also easily collect and store different kinds of data. So we have a lot of industrial big data now that facilitates our application of deep learning on the industrial problems. The second reason is the development of the hardware. For the typical algorithm, we usually use the CPU for the computing, but it is not sufficient. It is not very efficient. And in the recent years, the GPU has been well developed, and that is about parallel computing. And a lot of many difficult computing problems can be solved using the latest GPUs. So it helps us increase our computing power. Another reason is the development of the softwares. Deep learning, even though it is not very complicated, but it requires a lot of computations in different layers of neurons. We cannot actually build the model by our hands from the very beginning. We need some tools to facilitate our use of deep learning. And in the recent years, many big companies uh, have come up with the software platform for the programming. So that is very easy for us to use the platforms for the programming, such as the TensorFlow and the Keras that we'll be describing for. So, what is exactly deep learning? I think the most accurate definition of deep learning is that it is that deep learning is actually representation learning. It learns another representation of the data. For example, in the left, we see that we are given the red curve and the blue curve. And now our task is to draw a straight line to separate the blue curve and the red curve. And we can see that in the original data space here, we basically cannot draw a straight line, or very difficult to do the task. But we can learn another representation of the raw data. We can do some projections, some mapping from the original space to a higher level space. Like we can do a mapping from here to the middle figure. And the red curve will be like this, and the blue curve will be like this. And in this representation space, we can easily do the task. We can use the straight line to separate the blue and the curve. So this task can be finished in the higher level data representation space and not in the original space. And we can also project the data space back. And this is our decision boundary. And if we project the space back to the original space, we can see our decision boundary is like this. So deep learning basically learns another representation of the raw data. It can help us to to address many problems that is very difficult or even not possible in the raw data space. And next, I will introduce some basic computations about deep learning. We know deep learning is basically the more advanced term of neural network, and this shows how one neuron works in the network. First, we are given some input data, like here we got given the x1, x2 to xm. And for one neuron, we do the computation like this. We got different weights correspond to different input. We got omega here, omega 1, omega 2, omega m. And we do the very simple computation here. It's just a weighted sum. We multiply x with the corresponding omega, and then we add them together. So it is basically a weighted sum computation. And we can also use the bias term for the computation. And we can see that here it is just a linear computation. It's not enough to learn very advanced, very powerful representation. So in order to increase the representation learning performance, we also use another nonlinear activation function to do the computation. So it is very simple for a neuron to work. It's just a weighted sum here and another nonlinear activation here. And we got the output. And for the nonlinear activation functions, we have a lot of choices. These are the three very popular choices of the nonlinear activation functions. One is the sigmoid, and the other is tangent. And they are both of course, very effective, but pretty old activation functions. And in the recent years, the the rectified linear unit activation function is very popular, especially in the image processing, the speech recognition, the tasks. And even though it looks pretty simple, it's just a straight lines for the activation, but it is very powerful. And the nonlinear part is lies in here. If you don't know much about deep learning and you want to play it, you can just use ReLU as your activation function. It usually gives the best performance. And we know how one neuron works, and next we will combine them into a layer. So we see here that this is the input, and this is one neuron as we talked about previously. And one neuron, the computation is just a weighted sum. And we can put multiple neurons together in one layer, and then we get a hidden layer in the neural network. For example, here we got 4 neurons in this layer. And for each neuron is just a weighted sum computation and a nonlinear activation function. So the 4 are similar. They just have different parameters of the weights for the computation. And we can see that for one neuron, it is a weighted sum. And for a hidden layer with multiple neurons, it's just a multiplication of the matrix. And this is the weight matrix, and this is the input. So for each neuron, it just do the basic weighted sum, and we combine them together to form a matrix multiplication. So it is also not very difficult. And we see there are a lot of parameters in the neural network. We got a lot of weights, a lot of biases. So how can we determine which parameter is the best? That question is, how do we train our network parameters? So that's how to introduce a term like as a loss function. Loss function is very important. It quantifies the gap between the predictions and the ground truth. That is what we want our model to do. For industrial applications in condition monitoring of the machines, there are mainly two kinds of the regression, and the other is classification. For regression, one of the most popular example is the remaining useful life prediction. Based on the condition monitoring data, we want to know how much lifetime there is left for the machine, and it is a regression problem. We want one value at the end. And the other one is the classification. For example, is the fault diagnosis of the machine. We want to know which fault mode is the machine currently. So for these two type of tasks, we usually have different loss functions to use. For the regression, we usually use some loss function like the mean squared error. And we see that it is pretty simple. For example, this is our ground truth, and this is our prediction. We just want our prediction to match the ground truth in our inference process. So we just want to minimize the mean squared error to achieve the optimal prediction performance. And for diagnosis, the classification problem, it is more complicated, but the implementation is also very simple. We usually use the cross entropy loss to use in the classification text. The math description is like here, and in actual implementation, it's not very difficult to use because there are already some packages for you to use. So are the two most popular loss functions here. So the training process of the model establishment is like this. We want to update our weights and biases to decrease the loss function. So there are mainly 3 steps. First, we forward parse to compute the network output and the error. That means we are given the input, like here, and the network parameter are fixed or initialized as a random number. Then we forward parse the input to the network, and then we get the output. Then we know the output here is our prediction, and we compare our prediction with the ground truth to calculate the error. And we know the error. We want to minimize the error. So the next step will be backward parse to compute the gradients. That means the gradients of the weights and biases, the parameters. That means in which direction the parameter will be updated in order to minimize the error. Our goal is to minimize our loss function. And then we get the gradients. So the final step will be we update the weight, the parameters based on the gradients we have. So through the iterations of the 3 steps, through multiple iterations, and we can gradually achieve the optimal point in our model. That means that is the whole process of the model training. It is like this. For example, the blue curve here is the loss function, the loss curve, and our initial solution is like here. For one step, we get the gradient and we optimize the parameters, and our loss function decreases to here. So we manage to decrease our loss function. But one step is not enough. We have to use many steps. In deep learning, we usually call it epochs. We use many epochs, so we gradually achieve the optimal point in the loss curve. And in this case, is the minimum value in the loss function. So it is the training process of the model. And this one shows an example of the optimization of the model. For example, our task here is to feed the 4 points, the 4 red points as a curve. And the red figure here is our optimization process. The white point is our solution. We can see that our solution is first randomly distributed at the surface, the loss surface, the surface of the loss function. And through the optimization, the minimization of the loss, it's gradually approaching the minimum point in the loss curve. That we can see the curve will be fit better and better through iterations. One of the most important things in model training is the overfitting phenomenon. Overfitting is not good. Uh, Overfitting is not good. For example, in this text, we are given the task of to separate the blue curve and the red cross. And if we use the decision boundary like this, we underfit because there are many misclassifications here. And if we do the decision boundary like this, and it is pretty good. They are well separated, even though we have some misclassifications here, but that's reasonable because the data usually have some noises. But if we 100% feed the data, that is not good. That is overfitting. That means we may fit the noise in the data. That is, of course, not good. And the general pattern will be like this. So through the optimizations, usually we train the model using the training data, and we want to minimize the loss function, the loss value of the training data. So it can be of course minimized. But the test data will not be the same with the training data. So there should be a point, an optimal range where the test loss function will also be very small. But if we overfit the training data, in the late stage, the testing error will be very high. So that means we overfit the training data that cannot be well generalized to the testing data. And this is one of the example of overfitting. So suppose we are given the images of, like here, our training data is two cat images and two dog images. And if our model actually overfit the training data, so we are in the testing phase, we are given the image like this, and the model will tell us it is a cat. But of course, it is not good. You can have a guess why is the case. That means the model overfit the noise in the data. It doesn't recognize the image with the true physical meanings. It overfit with the backgrounds. If it is a white background, then the model will consider it as a cat. If it is a green background, it will be recognized as a dog. So we are given the testing data like this. Will have a white background and it is a cat in the eye of the model. So it's absolutely not good. Besides the traditional neural network structure, we can have many advanced architectures. For example, the basic one is the multi-layer perception. It just connects many neurons in different layers for the inference. But it's not very efficient because there are a lot of parameters here, a lot of connections. That means our model has too many parameters. That's not good. That is more likely to be overfitting the training data. So one of the very advanced structure is the convolutional neural network, CNN. CNN has fewer parameters and more efficient in the training, and it has less chances to overfit the data. That's good. That has more generalized ability. And the computation, the specific algorithm of CNN is also not very difficult. It uses many filters to slide over the input to get the output. For example, here we get the filter like this. It is 3 times 3 that filter. We have 9 parameters here, and this filter will slide through the input data. For example, now it's here, and we correspond the 9 parameters here with the area here, and we also do the weighted sum to compute a specific one value as the output. So the basic algorithm is still the same with the traditional neural network. And using the CNN alone is not can be further improved. Usually, we use the pooling layer after the convolutional layers to further increase the computation efficiency. The pooling is even more simple. For example, this is the input data, and we want to extract the most significant features for the later use, and also reduce the dimension because we got too large dimensions of the data. We want to minimize it. So for different regions, we just extract the largest value. It is one of the most popular operation, the max pooling. And we can also use the average pooling to extract the average value of each area as the output. So it is also a very simple operation. So by using the convolutional operation and the pooling operation, we can make the algorithm very powerful and efficient. And this is the illustration of the convolutional neural network. And we can also use multiple features in one layer. In the previous slide, it just shows how one filter works. And in each hidden layer, we can use multiple filters to extract different kinds of features for the later use. So that will be better. And even though deep learning is kind of complicated, but it is easy for the programming part nowadays because many packages can be readily used for the programming. Two of the most popular platforms for the programming, to the languages are the Python and MATLAB. Probably Python is the most popular now. It has many rich resources for the programming. And you can also use MATLAB because many students are more familiar with MATLAB. It has a deep learning toolbox for you to use. But many open source codes and the latest research results have been published using the Python. So if you want to dig deeper into deep learning, I suggest you to use Python for the programming. And in Python, we do not just use the basic Python to build a wheel for the model establishment. We use some platforms. Two of the most popular platforms now, one is the TensorFlow developed by Google, and the other is PyTorch. They are both very popular now. You can use either of them, and they are kind of low-level programming for the deep learning. If you just want to use deep learning for a straightforward application, not for research focus, you can just use Keras within the TensorFlow platform. So it is a more high-level API, very easy for the programming. Keras is also very easy to learn. You can just go to their official website for the to learn the programming of Keras. Their official website is like this, and we can see the menu here. There is getting started, 30 seconds to Keras. Actually, if you follow this, you can actually get started in 30 seconds. It's really simple and basic. For example, this is a complete deep learning model code for a specific task. We can see that it's just so few lines of code. It's really easy to read and not very complicated, but it is already a well-established deep learning model. So using Keras, you can easily build a model by yourself. Next, I'll talk about the actual applications of deep learning in the condition monitoring industries. So deep learning has achieved a great success in some tasks like image processing. It is also very successful in our area, in our industrial applications. For example, in our problems, we are usually given the data of the condition monitoring data like vibration data, current data, acoustic emissions, and sometimes we are given the images. And we can use the data directly as the input to the model. We don't have to extract many features. That is a relief of the feature extraction part. And it can directly give us the output. That depends on what we need. For example, in different tasks, we may need different kinds of output. For diagnosis, we need the classification output, and for the prognosis, it is the maybe regression output. So it is a very straightforward and simple flow of our problem. And this is one of the example the for diagnosis of the bearings. This is the raw data, the vibration data of different health conditions of the bearing. There is 10 conditions. For example, this is the healthy condition of the bearing. This is the incipient inner wrist fault and medium inner wrist fault, and also some roller fault and outer wrist fault. So in different bearing health conditions, we collect the vibration data, and we can see that it is pretty messy, and there is actually a lot of noise in the data, either from the sensor or from the machine. So if we extract the handcrafted features, it will be pretty time consuming and sometimes it's not effective. So we could just use deep learning for for this problem. And the flow is very straightforward. We just put the raw vibration data as the input, and directly give it into the model, and the model will directly automatically give us the output. The model will tell us what kind of health condition is the bearing now. So it is pretty simple and also efficient and automatic. It builds a straightforward relationship with the input and output. So for some users who may not be very familiar with the for diagnosis or signal processing techniques, he can use the deep learning for their applications. And this is another case study of the using the IMS Bearing Dataset. It is also a public dataset. It collects the vibration data of the bearings in the accelerated life test, and it also has the data of different health conditions, like the healthy condition, auto risk fault failure condition, something like that. And specifically, we will have five health conditions for investigation. For example, the normal condition, the insufficient fault condition, and medium fault and advanced fault. So we got the five conditions of the bearing, and we prepared the dataset for our test of the algorithm. And we follow the traditional way of the dataset split, like the training data, validation data, and the testing data. And this is an example of the complete deep learning model using Keras. As shown in the previous slides, it's pretty simple, just maybe around 10 lines of code. So it's very straightforward to use. And different parts are also very easy to understand. So for Python, we first import the packages and then we read the data. We should set some hyperparameters for our model. Actually, for deep learning, there is many hyperparameters, but we can just make the problem very simple to use the default setting for the other parameters and set only the very important ones. Then for the model development and the compile and train, there's just so few lines of code. And afterwards, finally, we do the testing. So it is pretty easy for the programming. And this is the result in this case study. And we can see here the model accuracy. The blue curve is the training accuracy, and the orange curve is the testing accuracy. We can see that through multiple iterations in the optimization, the training accuracy will gradually approaching 100%. That is reasonable because we can always overfit the data. But the testing accuracy is usually not 100%. That means the training and testing data are of course not identical. They don't have the same distribution. So it must have some gap in the generalization. And this is the model loss. We can see we can always minimize our training loss, but for the testing loss, there always has some gap in the generalization. So this is a typical display pattern in the training process of deep learning in the for diagnosis case studies. So that is basically about the basics of deep learning. If you want to know more about deep learning, here are the recommended textbooks. For the deep learning algorithm, I suggest you to read the book written by Ian Goodfellow, who is a very famous researcher in this field. And if you want to know more about the detailed programming, I suggest you to refer to this textbook about the hands-on machine learning with the scikit-learn and the TensorFlow. So that is about the basics of deep learning, and next I will talk about the transfer learning. Transfer learning is also very popular in the recent years. It is very practical and solves very challenging and practical problems in the real industries. Transfer learning means we want to transfer the knowledge across different domains because the traditional machine learning usually assumes the training and test data are from the same distribution. That means our training data is from the machine under some conditions. And if we want to use the model for testing, the testing data should also be collected from the similar machine under even the same operating conditions. That's not realistic because in the real industries, the machine usually have different tasks, different products to manufacture. So they may have different operating conditions. But in different operating conditions, the data, the characteristics of the data must be different. So that will lead to some deteriorations in the generalization ability of our model. So here, this figure shows the domain shift phenomenon. The training data is denoted as the source domain here. And for this case, we may have the two classes, the circles and the triangles. These are the two classes. And for the training data, we can, of course, train a model to separate them. We can 100% accurate separate the two classes. But our testing data, denoted as the target domain, is made from a different operating condition of the machine. So their data, the nature of the data must be different. So there will be some shifts between the source domain data and the target domain data. So that results in that our model, our classification model, it is less effective in the target domain. We can see here that a lot of misclassifies here. So due to the domain shift phenomenon, our model has low generalization ability in different conditions. So that is of course not good. One specific example is like for the bearing for diagnosis. Our training data may be collected from the rotating speed A, and our testing data may be collected from rotating speed B. So that is the domain shift. And we want to bridge this gap. So we want to use transfer learning to transfer the knowledge learned from here to the testing data. That will increase the generalization ability of our model. And one of the basic algorithm in transfer learning is the TCA. For the very simple task, it can achieve the pretty good results. For example, here we got the two domains for as the red and the blue here. And for the original data space, they are separated. So, by using the basic transfer learning, we can make them align together to extract shared features. But even though TCA can be successful in some basic tasks, but for the more complicated machines in the more complex conditions, it is not good enough. So deep learning also finds a way here. So deep learning based transfer learning has been very advanced. It is very powerful to address this problem. And one of the most popular and advanced solutions in deep learning based transfer learning is the domain adaptation. So we got two domains, the source domain and the target domain. They are different, but they are different in the original data space here and here. So that means our classifier will not work in the target domain. So one of the intuitive idea is that now they are different. What if we draw them together in the same area? Then our classifier will definitely work. So that is the idea of domain adaptation. So that can be realized in the deep learning framework because deep learning is just very suitable for the representation learning. In the original data space, the representation is not good, so we can learn another representation. And in that higher level space, the blue and the red are in the same area. So if we achieve this goal, then we can just transfer the knowledge learned from source domain to the target domain. And usually we use a metric for the optimization. One of the most popular one is the MMD. It's called the maximum mean discrepancy. It measures the distance between the source domain and target domain. You can consider MMD as the distance like here, the distance between the two domains. And our goal is to minimize this term in the higher level representation in deep learning. So if we minimize MMD to be very small, then they are considered in the same region. So that achieves the domain adaptation goal. So I'll introduce a case study and show how transfer learning works in our real problems. So this data set here is very popular in the Bearing for diagnosis. It is provided by the Case Western Reserve University, the Bearing Center. So in this data set, we are given the condition monitor data, specifically the vibration data of the bearing in different conditions. For example, it has in total of around 10 conditions. The healthy condition, the inner race fault condition, ball fault condition, outer race fault condition, and in each fault mode, it has different fault severities. So in this case study, we got a number of 10 health states to classify. And the data are from different conditions. For example, the data may be collected from different rotating speeds. Actually, this data set has around four rotating speeds. It is denoted as the HP. 0 HP, 1 HP, 2, 3. And in this case study, we formulate 6 tasks for the transfer learning. For example, in the task T01, that means we use data collected from the 0 HP as the training data, and data from the 1 HP as the testing data. So our training and testing data are from different conditions, different domains. That means the transfer learning, transfer the knowledge from here to here. So we can have different transfer tests. And we can use the domain adaptation methods in this problem. For example, this is a typical deep convolutional neural network architecture for this classification test. We can use layers like convolutional layer, pooling layer, convolutional layer, pooling layer, and then finally fully connected layer and the softmax classifier. And usually for the basic domain adaptation, we focus on the fully connected layer. We want to minimize the MMD matching in this layer between the source and target domain. And if they are merged in this layer representation, we can know that the knowledge, the shared knowledge about the fault analysis is extracted from the both domains. That is good, but not good enough. So in our research, we do domain adaptation in multiple layers. That means for different layers, we do minimize the MMD between source and target domains. That helps to further increase our performance. For example, this is the visualization results in this case study. And the blue and the red curve are from different domains. You can consider the blue curve. The blue circles are the training data, the source domain, and the red circle is the testing data, the target domain. So first we can see without domain adaptation, it means the basic deep learning. And if we do not use any transfer learning methods, and this is our visualization results, and we can see for some layers, the blue and the red are separated. That means even though we can classify the training data, the blue circles, that for the testing data, we basically fail because they are not in the same area. So our fault diagnosis knowledge cannot be generalized to the target domain. And we can see if we use the domain adaptation, here for the red column, and the blue and red, the data points, are basically in the same area in different layers. For example, in this part, they are basically in the same regions. That means the knowledge we learned from the blue, the training data, can be generalized to the testing data in the target domain. So that transfers successfully transfer the knowledge. And here is the numerical results. And we can see here the the red bars are the performance of our proposed method. We can see that in different scenarios, our method basically achieves the best performance compared with uh, different approaches. So, and in many cases, the testing accuracy is just about 100%. That indicates the effectiveness of our method. And the red figure is about the realizations. For the same color, different color means different house conditions. We want to classify different colors. And for each color, different shapes are the training and testing data. And we can see if we do not use domain adaptation, some colors are separated. For example, the red color. The training data may be from here, and the testing data may from here, the circle and the triangle. So they are not in the same area. That means the generalization performance will not be good. But using our proposed method, we can see that the different shapes of a certain color are in the same area. That means the knowledge are the same. The for diagnosis knowledge are the same for the source and the target domains. That intuitively show transfer learning is very effective in the classification tests. The bearing transfer learning problem across different operating conditions is pretty challenging, but there are also more challenging tests. We can not only transfer between different operating conditions, we can even transfer across different machines. For example, for this type of machine, we use that to collect our training data. And can we use the knowledge we learn from this data to different machines to test the bearings in different machines, but of course, the similar rotating machines? And for different operating conditions, when the operating speeds are different, we can see the source and target domain, they have some gap. But for the different machines, the machine A and the machine B, since they are different machines, so their gap are more significant. So this is more distance with the source domain. So the problem here is more challenging. So because the data, the feature gap are more distant. But we can also use transfer learning in this kind of test to transfer the knowledge across different but similar machines. And there are also some physical meanings behind this. For example, for the bearing for diagnosis, we usually use for the conventional methods, we may use the fault characteristic frequencies as our features for the diagnosis. And for the characteristic frequencies, they have some patterns. Like the outer race fault, it may have some impulses periodically for the machine. So even though they are different rotating machines, but they share the same data patterns. So we can try to extract the shared knowledge from different domains for the fault diagnosis text. And traditional domain adaptation methods minimizing the MMD term may not be very effective in this case because now we are talking about different machines. That is more difficult. So there is another way of achieve the transfer learning effects in this problem is to use the virtual learning. But the virtual learning is more advanced. Basically, they have different modules, the feature extractor, domain discriminator, some classifiers here. Through the adversarial training before the feature accusator and the domain discriminator, the more and more generalized features can be learned as high-level representations of the raw data. Then the classifier will take the learned features as input and do the classification. That is more effective in many cases, and that is possible to solve the more challenging problem. And for example, this is the results visualization in a case study. We see here that we use the data from different data sets as the input for investigation. For example, we use some chain body data, credit data, IMS data, and the case western data. If we do not use the transfer learning methods without domain adaptation, we can see that different colors, the data from different datasets are well separated. It's here, 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 because they have different patterns. For example, the vibration amplitude may be different, so it is very reasonable they are not in the same area. But that is not good for the generalization of the knowledge. For example, you use this data as the training data and you learn a classifier, but it definitely cannot work on these other regions, so your model fails. So we use adversarial learning in this problem and achieve the generalized the shared features across different datasets. And the visualization part is right here. We can see that different colors are projected in the same area in the high-level representation space. That means the shared features are learned, even though they are different datasets. So the knowledge we learn here can be generalized in different datasets. That is better for our testing. And for the numerical results, it's also validated that the blue bars are the proposed method. We can see in different cases it is absolutely better than the basic ones without any transfer learning methods. So we can transfer the knowledge across different machines. Another example is transfer learning across different sensors. Because usually we assume our data are collected by the same sensor, but in practice it may not be available because sensors may have some malfunctions. So what if in the testing scenario our training sensor just fails? We have to use the data from different sensors for testing. But absolutely, the data from different sensors are different. So we may want to transfer the knowledge across different sensors or similar sensors at different places. For example, here shows that we may have different sensors at the drive end and the fly end of the motor. And we want to transfer the knowledge learned from the fly end data to the drive end data. So that is another type of transfer learning. And it is also very challenging because they share the different characteristics. They are basically in the heterogeneous feature space because the different places may have different vibration patterns. So the source domain and target domain may be very distant from each other. But this problem can be also effectively solved using the latest technology, such as the adversarial learning. But in this case, we may have to use more complicated, more advanced architectures for the specific problem. And the result is also pretty good. And specifically, we can see the visualization results here that different colors also represent different health conditions. If we do not use any transfer learning methods like the source only method, we can see that the different shapes of a certain color are separated. That means the data from different sensors are actually different, and they are not projected into the same area. So the knowledge cannot be shared by the data from different sensors. But using our advanced transfer learning method that we can see, even though for some classes, the different shapes also have some noticeable gaps, but absolutely they are more closer now in this scenario than the other cases. So the classification boundaries can be better shared in this case. So we can still extract the shared knowledge across different sensors. The numerical results also validate our performance. Our proposed method significantly outperforms some baseline, some benchmarking methods in some cases. So that shows the transfer learning method is very effective in the practical applications. So that is basically about the introduction of deep learning and transfer learning in the industrial big data, the field. So these are some references about the deep learning and transfer learning in for diagnosis, remaining useful life applications. So if you are interested, you can refer to these papers for more detailed investigation of such methods. All right. Thank you.